My name is Tim Honeycutt. I worked for NASA for over 20 years. Most of that time was spent testing flight and ground hardware. This includes performing multi-element integration tests for the International Space Station program, as well as planning the integrated test and verification activities here at KSC for the Constellation program.
I'm Stephanie Sowards, and I have worked for NASA for about 23 years, and the majority of my career has been involved in integrated testing with the International Space Station program, where I had multiple roles and responsibilities there.
The ship and shoot philosophy involves shipping flight elements directly from the factory to the launch site without further testing. This philosophy has been around since the 1950s. Both NASA and DoD has used this in many of its programs. The International Space Station program adopted this in the early 1990s for many reasons. One of which is because they had geographically dispersed international partners that designed and manufactured the flight elements and space station hardware. And these companies and these organizations and these countries, of course, are all around the world. They not only developed this hardware at different times, but this hardware is also launched in a couple different places, the U.S. and Russia. So it made it very difficult to bring all these components back together and perform an integrated test at one time. There was a point, though, when there was a slip in the Russian delivery dates, which changed the launch date as far as the manifest. And at this point, the International Space Station management decided that it gave them an opportunity to perform an integrated test with the hardware that was currently being delivered at the launch site. There were multiple elements that were going to come here at the same time and start backing up because of the launch date hold. And since they had that opportunity, they decided to perform something called a multi-element integration test, which was a risk mitigation test.
One of the things that made multi-element integration testing, MEIT, feasible was that the Russian service module had a schedule slip for its delivery, and NASA management took that opportunity to conduct integrated testing, which was extremely wise. Given that the program initially chose a ship and shoot philosophy for space station, there was a possibility that there could be catastrophic outcomes due to the risk and the challenges that would have been experienced on orbit.
By definition, an MEIT is an integration test between two or more flight elements that are going to be launched on separate launch vehicles and integrated in space for the first time. It's a risk mitigation test that's performed on the ground for the purpose of validating the operations of these flight elements and their systems in an environment that is flight-like as possible. There are three primary objectives of an MEIT, and they are first to demonstrate the interoperability, functionality, and stability of flight systems, elements, and subsystems in an integrated in-space vehicle assembly, and then, of course, launched and assembled in space for the first time. The second objective is to validate the critical mission sequence activities and flight procedures, and the third objective is to collect performance and functional data to model the ISS vehicle.
Using risk-based analysis to determine if we should conduct an integrated test is a nice idea, and it looks good on paper. However, given the complexity and the tightly coupled configurations of elements that span geographical and international boundaries that could result in catastrophic outcomes, the right thing to do is always to perform the actual integrated test. MEIT was designed to test both mechanical, data, electrical, fluids, every subsystem across those elements. Even though there's a cost associated with integrated testing. There are ways to mitigate that cost and to reduce that cost. The first one is to ensure that the standalone elements and their components have been thoroughly verified at the factory before transporting to the launch site. The second item is to make sure the software is flight qualified tested before bringing to the launch site. Those two items are very critical because during an MEIT, that configuration is a very complex configuration. The procedures are more complex. You have more personnel there, and you don't want to use that particular scenario to drive out problems and issues that should have been found early on in the process. You want to reserve the MEIT for actual interoperability type problems and repairing those there. And then the third area is GSE, ground support equipment. The overhead associated with GSE can be very rigorous based on where it's being developed. Case in point, during MEIT, we had what was called the ISS flight emulator, and we would emulate just about any space station element that was needed based on the requirement for test. But what that meant, even with the slightest change or configuration change with the emulator, is we had to go back and reproduce a load of documentation and drawings that were unnecessary, and this drove the cost of just the GSE. So what we did about halfway into the flow is we devised a new method, and we called it the LUT, limited use test equipment, and what that did is it streamlined the GSE process, and we were able to save hundreds of thousands of dollars.
Some of the ground rules for performing MEIT would be that you would want to have all of your system level testing completed and all of the open work completed as far as getting the configuration correct on each element prior to putting it in the configuration of the integrated test. Also, you want to utilize the flight qualified and tested software such that you're using the same software that you're going to use, that equipment's going to use on orbit. So you ensure that it works the same way on the ground as it's going to be on orbit. The MEIT tests were definitely a collaborative effort. The international partners as well as the U.S. partners were greatly involved in these tests. The manufacturers of the hardware, we really encourage them to be a part of this test, to be here on site during testing, as well as the folks here that plan the test and execute the test. We also had the flight crew involved in running the procedures during the test, so they get the experience necessary so that when they get on orbit, they know what they're doing and can understand what they're seeing, as well as the ground crew, and we involve mission systems as well. Having the designers, the manufacturers here during testing greatly enhanced the test, because when we ran across issues, sometimes they weren't issues, and these manufacturers or designers would be able to quickly say what that data meant. Also, when we ran into certain problems, they were able to really do some analysis on those problems and help us understand what the problem is and how to resolve it. There were also additional tests that were performed, especially on critical systems, as well as checking the redundancy of other systems to ensure that when this equipment and this hardware is operated on orbit, that it works appropriately, and if there's any issues, then definitely we would have a backup or an emergency way of safing the vehicle.
There's another philosophy out there that says that integrated testing can be performed in a simulation lab or with emulators. And while that is a good risk mitigation step, it does not suffice for actual integrated testing with flight hardware. Case in point, the swapped video lines between the U.S. and Canadian segment. I don't think we could have ever identified that in a simulation lab.
For MEIT, because it's such an integrated test between large flight elements, Space Station is designed to be on orbit for many, many years. There's no way to test every scenario. So what we had to focus on was the activation sequences and procedures, the emergency procedures, as well as many procedures involving the day in the life in station. As far as lessons learned go, there were a number of significant problems that were found, that were identified and solved prior to launching these elements and operating them on orbit. Some of those would include, for instance, the activation of the U.S. lab. The activation was a critical activation. The requirement was to activate the U.S. lab in less than 2 hours. There were some thermal loading conditions that would actually destroy the lab if we exceeded that on orbit. And the first time we performed this activation on the ground, it took us 36 hours. So we had to really understand the computer problems we're having, understand the procedure changes in order to get that time down below 2 hours. And we ended up doing it in 1 hour and 15 minutes prior to launch. So that way, when we were on orbit, it took much less time, and we were having no problems with activating the lab. Another issue that was encountered was the activation of the P6 truss element. There was an auxiliary power converter unit that had a under-trip voltage condition, and we were not able to power up the P6 truss here on the ground during MEIT. If that would have happened on orbit, we'd actually had major issues of getting that going and providing the power to station, including bringing back hardware to the Earth, which would have been very costly. Another example would be the task overruns in the command and control computers. These task overruns caused the central system of space station for these CNC computers not to be able to command and control or to view health status of the vehicle, which could be catastrophic. So these type problems, we learn from them as far as finding them on the ground, resolving them prior to launching in orbit. If we would have had these type significant problems on orbit, we would have had major cost and schedule delays. It would have caused increased safety issues for the crew. We could have had a loss of mission objectives, loss of flight hardware. It would have driven unplanned EVAs. So for future programs, I would take all of this information into consideration for what we learned from MEIT, not only that we need to look at what type of integrated testing at the launch site that would be needed, but also the planning that it takes to put one of these tests together, providing all of the correct GSE, the right personnel, the right involvement of other organizations and companies and down to the manufacturer's level. To plan that up front is a great cost savings, as well as to catch these problems that we find on the ground, and we identify and resolve on the ground prior to getting in orbit. So some specific lessons from MEIT. One is the fact that we do know that we will come across unknowns when we integrate hardware together. There's no way of understanding all of the scenarios involved with large-scale integration of space hardware until you actually put the actual hardware together. You can simulate that, you can emulate that the best that you can, but there are some unknowns that you'll come across when you actually perform that final integration. Another example is that there is no substitute for experience. Both using emulators and simulators and getting the people involved in utilizing those and understanding the hardware is really good. However, utilizing the actual hardware in the configuration that you're going to have it on orbit is the best experience. And that's why we brought in the flight crew personnel, the astronauts, to actually run the procedures that we performed on an MEIT test, such that they get the experience before they get on orbit. And they get to see the problems that they may get on orbit and how to resolve those problems.
If during the design phase of flight hardware we would consider integrated testing, it potentially would facilitate performing that type of testing. And the reason being is it would allow you to overcome some structural limitations. It would allow you to simplify the hardware interfaces. Case in point, during MEIT, we could not hard mate the elements. And the reason being is some of the orientation of those elements was not possible on the ground. So as a workaround, what we had to do is we had to build somewhat costly flight-like jumpers and cables, and those were somewhat expensive. There was a lead time of about 18 months. So what that says is if we think about it early on, that possibly we could have design built in that would facilitate integrated testing.
Another lesson that we take into future programs is that it was determined that we really needed to test the connectors and cabling between flight elements prior to launch. A lot of these elements weren't here at the same time, so we couldn't connect them up. And because of physics, such large elements, we couldn't get them close enough to do that. But we had to use had to use cables to do that. But to utilize the on-orbit cables to check the clocking, to check the distances between the flight elements, to see if these existing flight cables would work, we found a number of problems, mainly because of the trying to understand the ICD. There were just different perspectives on what that ICD meant. So the manufacturer saw it one way, and of course, it was meant when it was written another way. So when we got them here, we found a number of clocking problems, distance problems that we were able to resolve. Another lesson that can be taken to future programs is that we use the latest version of software possible. You definitely would like to have flight tested and qualified software, FQT software. However, sometimes software does lag behind the hardware, so you're going to have to put up with finding problems that the software developers already know about, but it still behooves everyone to try to use that latest version. A final lessons learned would be really to understand your risk posture of how much cost and schedule you're willing to give up to try to mitigate certain risks that you have by not integrating this hardware prior to launch. Cost and schedule does matter. However, a program that has a good strategy for integrated testing prior to launch definitely would give itself a lot more confidence in the end goal of actually achieving their goals for the program. We took the lessons that we learned from MEIT within the International Space Station program, and we start to look at it and apply it to other programs. Within the Constellation program, for example, we really tried to understand what type of integration testing would need to occur here at the launch site. We noticed that the first stage, upper stage elements of the launch vehicle, as well as the spacecraft, the space capsule, and the service module weren't really integrated together until they, for the first time, they're going to be integrated here at the launch site. And so we developed a test similar to MEIT called the Flight Element Integration Test, FEIT, to take that into account in our planning up front, to try then not to put together a test late in the flow, which would cost more money, try to understand how we would need cabling or GSE, that sort of thing, but we'd actually plan up front to perform these tests to mitigate risk. And if someone has any questions about some of the future activities that would involve something like an MEIT, they could feel free to contact me. I'm currently at Kennedy Space Center, and I'm also listed in Global.
If integrated testing is something that you would like to pursue as part of your new and upcoming program, I would be happy to provide any information and knowledge based on my experiences. I can be reached at the Kennedy Space Center. My number there is 321-867-5957.